Right, so I've managed to get this argon laser fired up. I'll just quickly go through this and then turn it off because the fan's so noisy. I've just got it firing out at, so you've got this nice sort of turquoisey blue beam. I'm pointing at a diffraction grating so you can actually see the 8 argon lines from sort of green up to fairly deep blue. And it's pretty bright. It goes up to about 100 milliwatts at full power. Just quickly go over this. There's tons of information on the net about argon lasers, so I'm not going to go into any huge detail. It looks like the fan for this was external, but again presumably to avoid vibration. Because obviously to get rid of a kilowatt of heat needs a fair amount of airflow, so I just stuck this great big fan on the end and that seemed to work okay. And so inside we can see there's the main heat dissipation from the tube, the actual base of the tube with the filament. If I actually turn this on, you actually see the filament lighting up. And so that the filament current on these is quite high, typically sort of 20 or 30 amps or so. That's one reason for the chunky pins on the connector. Most argon lasers use this type of connector, so there's sort of 2 massive great pins for the filament and then the small pins for everything else. And we can see there's 2 sets of fins. This is the main heatsink for the main sort of cavity, but there's a separate isolated section. This is the anode, so this will be at plus sort of 100 odd volts, but also it'll have a high voltage spike on it when it strikes the tube. So we've got this connection coming in here, but that's sort of electrically isolated, so we've got some cooling, but it's electrically isolated from the rest because of the high voltage spike is a very rapid spike. You don't want too much capacitance on that, but also you want to make sure it strikes sort of all the way down the length of the tube, which is why they've isolated these 2 sections of heatsink. Down here we've got the igniter circuit, so that is very similar to the sort of igniter you see on discharge lamps and xenon lamps. It's basically a choke where the anode current passes through a winding, and then there's another winding that induces a high current spike on top of the main anode voltage. And these are typically a simple capacitive discharge circuit, so we've got a big capacitor there. Down there is almost certainly a thyristor, so it just charges up the cap, fires the thyristor to provide a current spike into the primary of that transformer. On the top here we've got a little circuit here which is the optical monitoring. There's a photodiode in here, and there'll be some sort of beam splitter, and then just a little amplifier circuit to produce a voltage proportional to the optical output. Down here there's a capacitor. I'm not quite sure what that's connected to. Can't be bothered unbundling all this cable loom. And I was a bit curious as to what this down here is. There's a little block on a PCB, but nothing obvious coming out. Now, taking the back cover reveals this is actually a runtime counter that they haven't bothered putting a window in the back cover for. So whether that's a sort of slightly covert one for to check the service hours when they're servicing rather than an end user visible. I'm just surprised they didn't bother putting a hole through the back cover for that. Power up, it's showing 2,126.8 hours. I don't know what the normal lifetime of these is. I have seen a few messages on the net saying that these are actually quite unreliable. There's a few people saying they've had them fail within a year on new Leica setups, which is a bit disappointing for an expensive bit of kit like that. And at the back here you can see this is the rear mirror, fully reflective mirror on the laser. Obviously it's quite transparent because it's designed to be only reflective at the specific laser wavelengths. Label warning you about beryllium oxide. They use that to get good thermal transfer on the main cavity, so they have beryllium oxide in there, which is hazardous if you sort of smash it and powder it, but as a solid it's not too big a deal. Right, take a quick look at this power supply. There's a connector on the front which has all the sort of controls, interlocks and so on, and there's a couple of adapters. This is just providing an interlock loop, and this is just a dongle box with various pin out adapters. And this goes through to, say, there's some interlock stuff. One interesting thing, I noted the pressure switch on the air duct wasn't connected, or it looks like it was supposed to be. There's this thing that says vacuum switch with 2 things. This was just taped over, so maybe they had issues with getting enough airflow to trip the vacuum switch and just bypassed it. So that's a bit dubious. And the rest of the cable which goes up to the front panel, it's just a power control pot, and there was the key switch I just wired across, sort of quite over the top mounting. So this is just a normal plastic pot. They've made this massive great chunk of aluminium just to mount it on the front panel. But then again, they weren't too concerned about cost on this thing. And the backplate of this shows output 70 to 150 volts DC at 3.5 to 9 amps. Pretty well packed inside. There's this transformer on the top, which I'm guessing is probably just an auxiliary supply or something. It certainly doesn't look big enough to be a filament transformer. And there's this massive choke. All this here is just the input filter. There's a relay there. I'm not quite sure why they've got a relay there. It may be some sort of interlocking thing. And sort of two, maybe three vertical boards here. And there's a base board that's got some massive toroidal chokes on it. Huge capacitor there. We've got this massive great heatsink here with the fan at the back. So it's sort of ducting air through here, then out through this side vent here and through here, through the side here. I'm guessing most of the semiconductors are going to be on this heatsink. And taking out that board, so we can see these two. You see these two massive inductors. So a transformer there. A few more inductors. So this thing's basically sort of big buck regulator, effectively, with a few extra control bits in there. There's a couple of inductors there. I'd imagine these are probably to do with the filament supply. Again, that's probably a little buck regulator to provide a low voltage at very high current for the filament. Let's look at these helium neon tubes. There's this little board connecting. This is just a simple power distribution board, some relays, connections for each output, and some fuses. There's two fuse positions that they're marked as for 12 and 24 volts, so they use different fuse values, and for some reason they put them in different sockets. And they use these sort of potted little power supplies. This is pretty common for helium neons. And these are Alden power connectors, which have got sort of very long creepage distance for the high voltage. And so the red helium neon works quite happily. It puts out about 23 milliwatts. So this is quite long as helium neons go. But I mean, helium neons are fairly obsolete these days because obviously a lot of the applications have been replaced by diodes. They do have some advantages. They do have very nice beam quality. You get sort of very nice low divergence beam and a very stable wavelength at 632.8 nanometers, which is often used as a wavelength reference. Now, unfortunately, the power supply for the yellow one does appear to be dead. It draws a huge amount of current. I've tried connecting the yellow tube up to the red power supply, which is actually a high voltage supply, so I would expect it to do something, but it's not drawing any current, so it looks like the tube isn't striking. So could well be that tube is dead. I'll give it another go on a different HV power supply, but it's a real shame that, I wouldn't have been bothered if it was the red tube that was dead, but the yellow Heenies are pretty rare, so it's a bit of a shame if this thing's not working. So I was just sort of taking a look at this thing just to see how easy it would be to actually open this up on the assumption that it was fried. I noticed this front piece was actually a little bit loose. You could actually move and was loose. So I sort of pulled it out and basically found the remnants of some rather burnt up resistors. Now these are the ballast resistors. Helium neon tubes, like neons, when they strike the voltage reduces, and as you increase the current the voltage actually reduces across it, providing a negative resistance characteristic. Now that will cause stability problems on the driver, so what you need to do is add a series ballast resistor which is at least as high as the negative part of the resistance characteristic to make it stable. And these are actually glass bodied high voltage resistors. There's three of them. One of them is still intact to measure 22k, so sort of 66k, assuming they're all the same value, 66k in total. And I know 68k is quite a common value of a ballast resistor for helium neon tubes. So I thought, well, maybe is it just these resistors that have gone? Because they were definitely open circuit, and obviously this has got quite hot, and it's actually looks quite sort of burned and melty in here. So these things have been obviously running probably hotter than they really should have been. So I just dug around to see what I had in the way of high voltage resistors, and I found that this is actually a carbon composition one. Although not specifically designed for high voltage, they're actually quite good, because most film resistors have got actually very low clearance distance on them because of the way they're manufactured. So this is an 82k, which is close enough. So I thought, well, let's give this a go, and bingo! We have a yellow helium neon tube working. So I just need to get some, I'll rebuild this properly. I'll get some proper high voltage resistors and rebuild that. But look, we have yellowness, which is a somewhat unusual thing. I'm guessing what happens to this power supply is if when the tube goes open circuit, the output voltage will sit quite high, because obviously these are normally meant to produce a high voltage to strike the tube and then run at much lower voltage. So I'm guessing what happened was, because of those open circuit resistors, this thing was running at high voltage all the time. The insulation broke down and sort of basically shorted out the and overloaded the output, that then caused the input stage to fry. I'd hope these things would have been a bit better protected than that, but apparently from what I've read over the years, these things can be a bit fragile. They're not particularly robustly designed. But so we've got the red power supply, and I think I've got another Heaney power supply kicking around somewhere, so I think I'll just maybe try and improve the design of this to improve the heat dissipation, and we've got ourselves a yellow laser. Right, so now to look at this solid state laser. So this is a 561 nanometers, which is sort of yellowy green. I think it's fairly close to the sort of colours of the earlier green LEDs before we got the true green ones. So not sort of really yellow, more sort of pale lime green. So unfortunately we don't have the controller for this. And unfortunately we do have the lead. So this is a nice expensive LEMO connector that then connects to a high density D connector that plugs into the controller that we don't have. So let's take a look inside. Obviously if you've got a good one of these, it's not a brilliant idea to open them up, because of that, if dust gets in, it can potentially cause problems. But this is a sort of fairly nothing to lose situation at the moment. So the connector comes in here. There's a flex PCB that goes onto that connector and then comes down both sides of the cavity. So we can actually see the laser diode here. I think the yellow part of the bottom is the actual laser, and above it there's another diode which is probably reverse protection, because laser diodes are super sensitive to static and transient damage, so it's not uncommon to find a sort of reverse protection diode actually on the die to reduce the chances of damage. And that goes through one bit of optics there and another one. And I think this central section is probably the main cavity. There's a sort of crystal in there, some sort. I don't really know too much of the details, but the general idea is you've got a sort of main lasing cavity and a frequency doubling crystal using all sorts of weird funky optics to double the wavelength. So this is probably about 1120 nanometers, then doubled to frequency doubled to 561. And then this goes through, there's an angled beam splitter here down to a monitoring photodiode to measure the output, and then that goes out to the output here. There's two blocks here. I think there's probably two thermoelectric coolers in here. There's some, you can actually see that the edge of the flex goes down here and here, but the fact these are two separate metal blocks would imply that we've got two separate thermal zones. One will be to regulate the temperature of the diode. That's not just about sort of pumping the heat away, it's about regulating a constant temperature, because with laser diodes the wavelength is generally dependent on temperature, and with a solid state laser it's actually quite critical to get exactly the right pump wavelength to optimize output. And there's a second thermal zone here which will be for the actual cavity, and again that tends to be temperature sensitive as well. So again that will be either held at a constant temperature that was determined at the time of manufacture, or maybe they actually cycle it to peak the output. I don't know. So yeah, I don't really have any more information about this. And there's a packet of silica gel in the end. Probably going to be an infrared cut filter on that output to reduce the amount of stray infrared. Now obviously these things aren't too difficult to get something happening by just putting some current through the laser diode, but when I was just sort of trying to probe out the pin connection to this cable, I noticed that across the laser diode was measuring a dead short. I thought, oh, maybe we've got a dead laser diode there. But I thought, well, it doesn't. I can't see any visible damage, and these things are fairly well protected, so it seemed a little bit unlikely that it would be a completely dead short. But one thing I was wondering, there is actually quite a lot of space in here, and knowing that these diodes are quite fragile, I was wondering maybe there's actually a relay in here that shorts the laser diode when there's no power. Which, it's not so. I've not really looked inside too many of these, but yeah, the fact that it was reading dead short but with no obvious sort of physical damage to it sort of suggested, well, that might be the case. So I unsoldered one of the pins and measured across, and yes, these two wires are measured dead short, but the actual diode itself, measures plausible for a diode. So clearly there is a relay in there. Now, it should be possible to figure out which of these pins, unfortunately the way this is all constructed, I suspect what happens is this back connector and this flex goes in first, and then the coolers and then the optical blocks go in second. Now of course I don't want to take these optical blocks out because that's almost certainly going to screw up the alignment, although I can't actually see any locking sort of resin or anything on these, but I'd really rather not touch that, assuming this is a working unit, because that's probably going to screw things up. Incidentally, I think the way these are actually assembled, so there's little blobs of glue around here, so I suspect what they do, there's also these sort of flat flanges, so I'm guessing what happens is all these get mounted into a very precise jig, they're moved around to line them all up, and then they're fixed in place with maybe a UV curing adhesive or something to actually lock them in place, which avoids quite a lot of lasers. You seem to use that sort of technique, which avoids the obviously the expense of having adjustments. And in theory, you know, as long as it's all locked up solidly when it's finished, it should make it nice, have sort of very good long-term reliability. So now we've established the laser diode is actually working. Let's stick some current through it and see what happens. I think, again, I've not played with too many of these, but I think the current through those diodes is of the order of a few hundred milliamps to a couple of amps. Obviously we know roughly what the output should be, so we can measure that, because obviously the only way you know what the limit is when when the diode pops, and we don't really want to do that. So we can certainly hopefully get it up towards its nominal rating. If we put the camera right up to the diode and start putting some current in, going up to about 100 milliamps, you can actually see it glow. And of course, I can't see that with my eye, because this is just the camera picking it up, and this is what's making it through the camera's infrared filter. If you actually want to look at this, the ideal thing is to use a monochrome camera which doesn't have a filter, and that will light up a lot more brightly. What I'm doing to power this, I'm just using a bench supply with a series resistor, so it's very dangerous to use the constant current mode on power supplies, because particularly, for example, if you set the power supply up to a certain current and then connect it to the load, you're always going to get a big current spike, because obviously the power supply is putting up out its maximum voltage until it sees a load. So if you just sort of set your power supply to say 500 milliamps and connect it straight across, you're almost certainly going to pop the diode. So the nice thing about using a series resistor, it puts a fundamental limit on the amount of current that can flow, and I'm just starting up from zero and just very slowly easing it up and until we actually see what the current is. Right, so as I increase the current, when we hit about 350 milliamps, we're starting to get a nice little laser spot on there, very, very dim. It starts getting quite a lot brighter, up to 800 milliamps. So this is the point at which I'm going to start using the my laser check to actually look at the actual power output from this. Well, unfortunately, I think I might have gone a bit over the top. It seems to have stopped emitting anything, and the forward voltage of the diode's just gone down quite a bit, so I think I might have popped it, but seeing as we didn't have the controller, it would have been quite a lot of work to get it working for a fairly feeble lime green beam. It's not slightly annoying, but not a huge loss. I suppose it might be worth trying to do what I don't know, because it's a slightly non-standard wavelength, whether it also uses a non-standard pump diode, because obviously a standard 525 nanometer laser uses 808 nanometer pump diode, and I don't know whether this uses the same or whether it uses something a bit more exotic, so I don't know how feasible it would be to put something different in there and still make it work. Now we're possibly slightly less concerned about its health, I might pull the blocks out and have a look at what's on that rear flex. One other issue is, from what I can gather, the power supply units and the heads are like matched pairs in that they calibrate them all as a matched unit, so it wouldn't surprise me if there's also an E squared on the that backboard with a serial number or something on it, so I think we need to take a look at that. Right, so this is the laser diode block. Both of these blocks look like they're machined out of solid copper. Incidentally, these red wires are for temperature sensors. There's a temperature sensor here, there's one measuring the base plate temperature, there's another one which might be measuring the other one further up. That's one of the Peltier elements for the laser diode. The second one's a bit of a fiddle, because the feedback sensor is sort of in the way of one of the screws, and that's sort of soldered into the flex. So it's a bit of a fiddle, so let's unplug these other thermistor connections. So that's the main cavity block. There is sort of coloured anti-reflection coatings on some of the optics in there. Again, we've got the temperature sensor there, and we've got the second Peltier color module there. Yeah, there's these two chips. There's a 24 LCO2 E squared prom, and there's another chip here which I can't identify, but it's only connected to I squared C and power and nothing else. So it's either another memory or it's a temperature sensor. Although, so I'm not quite sure why you'd need a temperature sensor with all the thermistors in there, unless it's to maybe get some sort of absolute reference to calibrate against or something. But brief look at other temperature sensors, but that's the pin out. I can't immediately find anything that matches it. I've just read that 24 CO2, there's nothing in it, so they haven't even bothered using it. Okay, let's take a quick look at this beam combiner unit. So this is the unit that combines the inputs from all the lasers. We've got the red helium neon, green, the blue from the argon, the sort of yellowy green from the DPSS, and the yellow helium neon going here. Each one's got one of these shutter assemblies on it, and this is a simple on-off shutter top on the back, because these are gravity returns, so by default they're closed. Small amount of current, they open up, so obviously the gravity return means they fail safe as shut, but also they don't need a huge amount of force to open, so you don't get a huge amount of vibration or heat dissipation. And what's in here from the back, this looks like it's a little DC motor that just turns so far and then stalls, and this only pulls about 50 milliamps at 4 volts, so it's not a huge amount of power. And if we shine a light through this backwards, we can actually see the colour filters. So if I just shine a white light through the output, you can see we've got the red, the blue, green and the yellow. So this is all going to be done through sort of dichroic mirrors and filters within this unit. And on the back you can see the beam path, so it comes in this way, hits this mirror, goes across through the shutter, then gets reflected down and then sort of combined. So these will probably be the dichroic ones here, which combine the different colours downwards. This diagram from the user manual just shows all the various laser options. So we've got the internal ones as well as external diodes, 430, helium cadmium 442, as well as titanium sapphire, external UV, argon ion and various other things. So some of these go directly into the microscope head and some go into this unit. Okay, I'm not going to take any of this any further apart just yet, because it might be useful to keep this all lined up for when I start playing with these acousto-optical things. I do now have some data from the manufacturer on these. They kindly sent me through the user manual on this, so a future video will feature some experiments for these to see if we can actually get them doing anything useful.